Thanks, Christoph, for the introduction, and welcome back all the people who were here yesterday and all the new faces I see in the crowd today. So, as Christoph mentioned, I'm presenting Climate Science 102 today. It's building on what we learned yesterday, but I'm going to do a short recap at the beginning so to get everyone up to speed, so everyone should be able to follow along. And to introduce myself, I'm Justin Bandoro. I'm a PhD student in the program in Atmospheres, Oceans, and Climate here at MIT, so that's part of course 12. And I study a part of the layer in the atmosphere that we learned yesterday, the stratosphere, so from 20 to around 40 or 50 kilometers up high. Okay. So today's topics, we're going to look at climate forcings and feedbacks. These are probably terms many of you have heard, but we'll look into them some more and to be able to understand them. We'll also look at what are global climate models, because these are what we use for predictions and also for better understanding what's going on or what has happened in the climate system. And parts of these that we'll look at are what's known as parameterization, so what we do on processes that are too small to be resolved in the model. And also we'll look at uncertainty. And then the last topic we'll touch on is the detection and attribution of human-caused climate change and how scientists can do this. So yes, so a quick recap from yesterday. What this plot is showing was the Earth's radiative fluxes. So you can think of this as the total energy coming into the system, and then how the energy is distributed by different processes within Earth's system, and then the energy going out of the system. So as we learned, there's around 340 watts per meter squared. So all these units are in watts per meter squared, so it's the energy flux through an area coming in. Roughly 100 is reflected back out. That's through both clouds and through the surface from ice, snow from the land, so there's 100 going back out. 79 is absorbed by the atmosphere, and so this is from ozone and oxygen, and this is absorbs in the ultraviolet. And then, as we learned yesterday, 161 reaches and is absorbed by the surface. And then the surface...
79 what?
Sorry?
79 what?
Watts per meter squared.
Oh.
So it's energy radiation that's absorbed by the atmosphere. And the surface, you can see it radiates up at 398, so double what's coming in from the sun. But this is because in the atmosphere, as we learned yesterday, we have greenhouse gases, and these absorb the long wave radiation from the surface, and they re-emit it both upwards and downwards, and so they re-radiate it back down to the surface. And since the pressure or density of air decreases exponentially with height, there's more coming back down to the surface than what's going up. And there's also this little window here where some infrared or long wave radiation can escape back out to space. So what's important to understand is this system should be in balance. So if you add up both of these, if you add up 100 and 239, you get 340. So that's roughly 340 watts per meter squared coming in and 340 watts per meter squared going out. But what we're going to look at today is what different factors can disrupt this balance of incoming and outgoing energy from the system. So you can think about this as adding more greenhouse gases, what would this do? And then also if you change the amount of incoming solar radiation, or if you maybe add some more clouds or other particles in the atmosphere that will reflect the sunlight back out. And this is basically what a climate forcings are. So it's the changes in the amount of energy that enters or leaves the system, and this then alters Earth's radiative equilibrium and can force surface temperatures or temperatures of the atmosphere to either rise or fall. And these can be either natural or man-made, and like we saw yesterday, we have the solar cycle, so that's an 11-year cycle, and where the output of the sun varies, and so that will change, if you go back, it will change this number coming in, and there's also changes in Earth's orbit, like the Milankovitch cycles we saw yesterday, but those are on much longer time scales from 20 to 100,000 years, and that will also affect the amount of solar insolation during the different seasons. And well, there's also other natural ones are volcanic eruptions. So again, like we saw yesterday, these are eruptions where you get input of sulfur dioxide into the atmosphere, and this condenses, and it's able to actually get up all the way up into the stratosphere, and then it condenses and forms particles that are like little mirrors that will reflect the incoming solar radiation back out to space. So that will, these are all examples of natural climate forcings. And then you can look at man-made ones. So these are ones shown here in red. And these are pollution, so aerosols. So when we emit pollution, these can also form little particles, and then they can have the same effect similar to volcanic eruptions. So it can reflect solar radiation back out. And these can correspond with what we'll see as a negative forcing, but then you have these positive forcings, such as from greenhouse gases. So you put more greenhouse gases into that atmosphere, you'll have more radiation coming back down to the surface. And there's also, you can think of land use changes, and deforestation are also man-made, or also called anthropogenic climate forces. And so yes, so
Could you mention the last word in deforestation?
Deforestation.
Yeah.
So you can think about this as like cutting down forests, and that will change the surface albedo. So it's how much more sunlight will be absorbed by the surface as compared to if you have a canopy, that will reflect more. And so it's changes in albedo, or how much is reflected from the surface.
Thank you.
And so a positive radiant forcing, so more incoming energy warms the system, while a negative one, which corresponds to more outgoing energy, cools it. And qualitatively, these are given as changes in the energy flux at the top of the atmosphere. But one important thing to take into account is that this does not entirely predict the climate response. And this comes back to feedbacks, which we'll touch on later. But I want to first give an analogy to what a climate forcing is, and this is a simple one that will help you understand. So you can think of it having a bucket with water flowing into it, and then it fills, and then you have a little hole at the bottom with water flowing out of it. And after a while, if we leave this on at a constant rate, it will reach a certain level where the level will be constant, and then the amount of water entering will be equal to that coming out. And if you can think of this in terms of the Earth system, the water flowing in is the incoming solar energy. What's coming out is Earth's outgoing long-wave radiation, so that's what's coming back out. And this level here is analogous to the global heat content, so how much heat is in Earth's system. And in a steady state, once again, the amount entering is the same as the amount leaving. However, you can think of these examples for radiative forcing. It's, say if we were to block this off a little bit and make the hole at the bottom smaller, that would cause the level in the bucket to rise, and so there'd be more water in the bucket, until it will rise until it reaches a new equilibrium. And you can think of this as a positive forcing, such as if we introduce greenhouse gases to the atmosphere, where it impedes the escape of long-wave radiation to space, so you have more of it coming back down, and then the level rising will be similar to the surface temperature rising. So this is a good analogy. So what are the different forcings? So this is a figure from the most recent IPCC report, and as mentioned yesterday, it's an intergovernmental panel on climate change. So this is where they assimilate all the reports or the current understanding of science of climate change into a report every 5 to 7 years, and this one was in 2013. And this is showing quantitatively the radiative forcing associated with different anthropogenic and natural forcings. And this is all relative to 1750. So on the top here we have mixed greenhouse gases, so we have CO2, and then all the other ones, which includes methane, nitrous oxide, and halocarbons. And these, what's important to also note here are the errors, or not the errors, the confidence intervals associated with this. So this shows a 5 to 95% confidence interval, and so you can see how much certainty we have on the amount of radiative forcing associated with these particular gases. So we can see that CO2 is has around just over 2 watts per meter squared, so that's additional energy coming into the system. And these other gases all are a bit less, but it's still net positive. And then there's also the effect of ozone, and has both in the stratosphere and in the troposphere. And you can go through all these. So there's surface albedo, and that's associated with the land use change I was talking about earlier. And you can see for some of these, such as the aerosol radiation interaction, so these are emission of aerosols, so pollution, and you can see just how big the uncertainty is associated with this. And this is because we're not sure how these aerosol particles affect cloud formations and where these clouds form, so if they're low or high level clouds, and this will affect the magnitude and the sign of the radiative forcing. So you can sum them, it reaches over to 0 here for these aerosol cloud interactions. But if we sum up all the anthropogenic ones, we have a net positive, just under 2.5, and with uncertainty from around 1.2 to over just under 3.5. And you can compare this to what we know of the forcing from the sun. So this is a change in the solar irradiance. Actually, this includes both orbital and the solar cycle. And you can see since 1750, it's it's very small compared to the total anthropogenic forcing in the climate system.
And the shaded areas represent, the shading represents uncertainty?
So this is, shading, so this one's just showing the troposphere versus the stratosphere.
The shading itself represents uncertainty, doesn't it?
Oh yes, so that represents,
as compared with the solid bars.
Yeah, so like, trying to figure out exactly that. Yeah, there's uncertainty associated with that as well. Can't remember, but the solid bars are the 5 to 95% confidence interval. So the next thing that we're going to talk about are forcing feedback. So this is so these feedbacks is showing a little chart showing what they are. They're internal climate processes that can either amplify or dampen a response to initial forcing. So say if we had any one of these, to go back, if we had any one of these forcings, how would the climate system respond? Because as we'll see, there's many different feedbacks where it can either amplify, so it means the surface temperatures might get warmer than they initially were from the initial forcing, or they might be dampened, so they might prevent it from warming as much from these feedback processes. So positive feedback will increase the initial warming, and the negative feedback will reduce the initial warming.
So positive feedback here is a bad thing, isn't it?
I don't know if it's, well, it's one that amplifies the initial response.
But since that means a warmer climate,
Yeah, you
in the
can,
present context, it's a very bad thing.
yeah, you could
So
associate
have
it
something
with
that's bad
but-
called positive is just difficult for me to wrap my
I see
head
where
around.
you're coming. Yeah, you can label it, but here we're going to stick to positive and negative, just because we'll see how it works, just the amplification of it. So an example of the positive forcing or positive feedback is this ice albedo effect. So say we have a positive radiative forcing, this causes surface warming, and then associated with this you have melting of ice, glaciers, and snow, and then that you can see after the ice retreats you have a much darker ocean and you have a darker land, and that will absorb more of the incoming solar radiation, and that will come back and amplify the initial surface warming. So this is an example of a positive feedback. An example of a negative feedback has to do with the temperature lapse rate. So like we saw yesterday for the structure of the atmosphere, so you can just think of this blue curve. The temperature decreases in the troposphere from the ground up to the tropopause. And what we know...
What's the troposphere?
Oh, so it's a layer from 0 to 10 kilometers.
It's below the stratosphere?
Yeah, below the stratosphere.
Okay,
where temperature decreases with height. And in future climate, we know that the amount of warming isn't uniform across all the troposphere, where it warms more in the upper troposphere compared to closer to the ground, and this has to do with changes in water vapor. So this increase is higher up than at the surface, and what this causes, so the warmer air up high can radiate more heat away to space more easily, and so that means you're losing more energy, or you can think about it as losing more energy than if it warmed, if you just shifted it and it warmed uniformly with height. And so this is primarily in the tropics, which covers most of the area of the Earth. And so we can think about this. You have introduce a positive radiative forcing, you get troposphere warming, you get a decrease in lapse rate. So this is the lapse rate, and so decrease means it doesn't fall off as much with height, and this means you get more increased cooling to space, and this will feed back to dampen the initial warming. So there are examples of all these feedbacks in the climate system, and this is what this figure shows. So a positive is one where it intensifies the initial warming, and then the negative is the negative feedback. So like we saw snow ice albedo, but there are also other ones with peat and permafrost, water vapor changes, cloud changes, ocean circulations, and this bottom part here might be hard to read, but it's showing the time scale associated with all these different feedbacks. So it ranges from anywhere from hours to centuries long. But how can we understand, how can we estimate Earth's response with so many of these feedbacks going on? You can see just from here, it's a very complicated system. And this is where global climate models come in. So given how diverse and all the different processes in the system, how do we make a quantitative assessment about climate change? So we can do it, so we can picture the Earth, if we divide the Earth up into small little grids in 3D, like in latitude, longitude, and also in height. So you have a 3D grid. And then we know the governing equations for fluid motion, radiative transfer, and then we also have chemical composition, and we can calculate all of these equations and how it evolves with time through partial differential equations in each grid box. And then we can solve it. And there's also processes that are, like I mentioned earlier, they're parameterized, so these are ones that are subgrid scale. And I'll touch on this in a few slides on how we can deal with these processes that we can't resolve. So if you think about it, if we have an area that's maybe like 200 by 200 kilometers, we're not going to be able to resolve like a cloud that's significantly smaller than that area, like a single cloud. So how do we have to figure out how we do it, how we can deal with these processes. And so it's a fully coupled, so these climate models are fully coupled, and this means that they have different systems working with each other. And so there's an example, you have the atmosphere, ocean, land, sea ice, and by coupling they're talking to each other. So they can send information what's going on in one to another system, so that the whole Earth system is in sync and coupled or talking with each other. And this is really neat because we can apply changes in external forcings. So say if we just add in the solar cycle, we can see how the system responds to just the solar cycle. Or we could add in greenhouse gases and see what happens, and similarly volcanic eruptions. And this is interesting because we only have one Earth. The Earth we only have one Earth now, and we can't do these cool experiments with it unless we find another planet that has like exact same conditions but maybe doesn't have greenhouse gases. But so this provides a virtual laboratory for experimentation. And this is showing how the complexity of global climate models over time. So this is showing at the first assessment report, so the IPCC's first assessment report, and then going through to AR4. It doesn't have AR5 in this one, but you can see the grid scale changes from these grid boxes were around 500 kilometers, and then now they're below 110 kilometers. And then going through with time, at first it was only an atmosphere and ocean, and then they started adding in different components to the model, and you can see sea ice, and then added coupling, aerosols, dust, carbon, biogeochemical cycles, ice sheets, marine ecosystem, adding in an upper atmosphere, and also atmospheric chemistry. So they've gotten more complex with time, and this scales with our computational power, because that's what it allows us to resolve or have all of these more complexities in the system.
When you say these different areas talk to each other,
Yeah, so they're
you
coupled.
mean they influence each other?
Yes, that's exactly what I mean.
Okay.
So like the temperature in the atmosphere can influence the temperature at the sea surface of the ocean, somewhere like that. So giving So to give an example of parameterization, like I talked about before, these are these processes that occur at small spatial scales that these models can't resolve. And so I'm giving an example here. So if we just took a photo of the sky and we see these clouds, we divide these up into grid boxes. So you can see in this grid box, if we look at in terms of total cloud area in the grid box, this one has very little, so we can put this as 0.1, the fraction of cloud, and then this one's 0.2, this one has a lot more cloud, so it's 0.7, and you can represent this one as 0.5. And so to do this, the physics needs to be represented, and then the grid box, but also empirically supported, so that we know what we're approximating it by is right. And so examples are cloud processes, radiative transfer, and boundary layer processes. So how we would do this is, in any given grid box, we know the average temperature, water vapor concentration, and pressure. And from these three variables, we can get an estimate of the relative humidity in the grid cell. And then we can use observations of, if you use observations of how we can derive statistical relationships between relative humidity, temperature, and cloud formation conditions. So this is what we can observe in the real world, and then we can transfer what we know into the model to parameterize this. And it's also important whether it's over land or ocean as well. And from this, we can get a cloud fraction in the grid cell.
What does that mean, cloud fraction in the,
Oh, sorry.
well, the percentages of
Yeah,
clouds.
so it's the fraction of percent. Yeah. So what percent of the grid box is covered by clouds?
All right, you covered that.
Yes. So the difference in how these subgrid scale processes are parameterized is an important reason why climate models differ from one another. So you can have one group, say over here in the United States, working on having their own model, then another group, somewhere in Europe with their own climate model, and they may choose to represent these processes in a different way, and that can have an effect on their results and their predictions. And that's what's shown here. So the CMIP5 is a model intercomparison project, and in here there's roughly 20 different modeling groups. And so to walk you through this, the black line, so this is global means surface temperatures, anomalies relative to 1986 to 2005. So these three black curves are showing observations, and you can see, and then the spread around it is the historical model spread, so how these models were able to historically capture the changes in temperature. And then this is the projection, so they can just keep on running into the future. And this is showing how much uncertainty there is with the future projection. And one part of it, the orange part, is internal variability. So like I talked about yesterday with El Nino, ENSO, and other internal variability in the climate system. But what you can see is this is the width of this uncertainty stays relatively constant with time, because they don't expect the variability to change, or the magnitude of it. But a large portion is also from model spread, and this has to do with how the subgrid scale processes are parameterized, like I mentioned before. And that represents a large uncertainty. But the largest one is the scenario spread. So RCP stands for representative concentration pathway. So we don't know how much greenhouse gases we're going to emit in the future. So we can estimate it. So say if we have business as usual and we keep on ramping up our emissions, we might get up here. But if we say we decide to cut back on all CO2 emissions, we might get something like this. So it just depends on what path we decide to go. But there's no way we can get this one, can reduce uncertainty and but unless we actually know what we're going to do in the future. But this one's the one that's the largest contributor to future temperatures.
You told us to ask about things like RCP?
Yes, so like I mentioned, it's a representative concentration pathway. So you can think about it, how much are emissions going to change in the future. So like you might have a high emission scenario where we just keep ramping up greenhouse gas emissions, or one where we level off and just keep it constant, or that's what's contributing to the spread in the future, and it gets larger with time. So the last part of the talk I'm going to focus on is detection and attribution of climate change. So just to get this down, climate change is the change in the state of climate that can be identified. So this is through statistical tests and looking at trends. So this is both changes in the mean or the variability and how long it persists. It can be decades or longer. And climate variability is the variations beyond just weather events in the mean state and other statistics of climate, like standard deviations or occurrence of extreme events. And both the variability is both on spatial, so looking spatially, and temporal scales. So detection is when we can, yes?
Is it possible to run through that again?
Oh, sorry.
With, I don't know, is there a different way to explain that?
So, so climate change, so if we observe, I'm gonna show it a bit more in detail in the next slide. I'm sure it might help.
All right, go ahead then, thanks.
Yeah. So you can look at the change versus the variability. So say we have a set of observations, so these can be anything. It could be temperature, precipitation, or just any thing or any measurement we have of the climate system. And we look at all these different ones and we pick out this red one. And we can see that it has a positive trend and that this trend is statistically significant. That's the detection I was referring to. But the attribution is more complicated because for detection we only need observations. For our attribution we need climate models to do this because it's establishing the most likely cause for these detected changes and that they're consistent with the forcing, and it can't be due to variability alone. So this can be, we have volcanoes, we have the 11 linear solar cycle, and we have CO2 emissions. And we can model it, and this is just showing if we put all these together in the model, what we get. So we can try to, this one looks like it's all from CO2 emissions, the trend we're seeing, but I'll talk about it more and how we can identify the human-caused component.
Do I see on that graph there was a period in which CO2 emissions went down? Oh, no, I mean the graph on the right. What is the graph on the right?
Oh, this is just showing temperature, probably. It's just showing it's just a cartoon example, but probably based on temperature.
So there was a temperature when we had
Yeah, I'm not sure
global
Yeah, so there
cooling.
was a period where it cooled a little bit, and that was due to all the aerosol pollution in the 50s and 60s. So you had lots of pollution, and you're able to regulate it. Because like I mentioned before, the aerosol and pollution is a negative forcing where it causes cooling because it's reflecting more radiation back out to space. But, so, to start off with detection, so how can we do this? So this is showing what we detected for climate change. So this is showing observed surface temperature changes from 1901 to 2012. And each one of these dots in here shows statistical significance at the 5% level. And you can see most of the globe, so these white spots are ones where you don't have sufficient records to say anything about it. But for most of the world where we do have observations, you can see there's been an increase in surface temperatures. But there are areas, like you see this spot here, where there's a cooling, even though it's not statistically significant, but this is the detection. So we've detected a change in surface temperature, and there's a spatially as well. And you can also look at it in terms of, if you look at mean sea level change, so this is from 1900 to 2010, and the same thing, the different curves here are showing from different estimates, so different data that's going into, that's like capturing the global sea level change. And you can also look at annual precipitation over land. And this one you can see, well, in these two cases, we can detect a change in precipitation. It's much more sparse. So like if you look at the speckling where the dots are, there's only some areas over the land where there's significant trends in precipitation compared to here, where it's much more robust response over the globe.
Can I ask a question about the map on the one on the left?
Yeah.
There seems to be a home in what is the Great Lakes area and the Great Plains of the United States. There seems to be a up there.
Right here?
Right there. Yeah, why would that area be, I suppose it's blank, not because of lack of observation, but because there wasn't
this
that
one
change?
it's showing like this color, right, blue. So like there's no statistically significant changes in surface temperatures over southeastern U.S. shown here. This is annual temperatures.
Whereas most of the blank areas are just like most of the Pacific.
Yeah, so
lack of
yeah, it's hard to tell, but like this one, we do have measurements, but whenever it's clear white, there's a lack of observations over the period. So like here, but like this area and that area, it's showing a small negative, slight positive, but not significant change. But yeah, it's hard here to see the difference between the lack of data versus what's significant. So how do we do the attribution of climate change? So how do we attribute the cause of what we're detecting? So first, we need observations of climate indicators, and this is what we just saw in the last slide. And then we need an estimate of external forcing, so how these external drivers of climate change have evolved both before and during the period of investigation. So before is very important because we want to know how it happened without without the human influence. We want to know how what the level of greenhouse gases were very pre-industrial before they started ramping up. So we need information on that, and also give an example for greenhouse gases and solar. And we need a quantitative, physically based understanding. So how external forcings might affect climate indicators, and we get this. This is where the global climate models come into play for the attribution. And it comes into here, and we also use them for the estimates of internal climate variability. So we need to just do these simulations that we'll see where you just have paleoclimate, or you just have the system running unforced, and just to see how many ups and downs in these indicators we can get, and whether we can ever get say a 50 or 30-year period that's corresponds with what we've seen in observations. And before I go into an example of it, I'll just say how the attribution of climate change has evolved over the various IPCC reports. So this is the first one in '95, and they say here, where it says the balance of evidence suggests a discernible human influence on global climate. And then you can go on to the AR2, where they say there is now new and stronger evidence. Most of the warming observed over the last 50 years is attributable to human activities. And then you can get to this one where it's very likely. And then the most recent one, it says it's extremely likely. So what has changed over all this? So one thing is that our observations, we have more observations, but they've also become better, where we corrected for any biases or drifts in these observations. So satellites are very prone to drifting. So even though we put them up there in orbit, they do drift with time. So we have to correct for that as well. And so we better corrected for these drifts, and also for stations on land as well, to make sure they're all calibrated to each other. And the big thing also is the advancement in global climate models and how we can model climate change. So I'm going to give a quick example before time runs out of one way we can do this, and this is called the fingerprinting method. And so we'll search for, so the way it's set up is that each one of these forcings has a different fingerprint on climate. So the one from greenhouse gases will be different from solar variability. And so we search for these different fingerprints and observations, and see how their signal has changed with time. So Right, so this is an example. So this is showing 1979 to 2012 atmospheric temperature trends. And there's a lot going on here, but I just want to focus on these bottom two ones. So these are from different satellites which have microwave limb sounders. So they've captured temperature data in the atmosphere. So it's showing it over from 90 south to 90 north, and also in height. So it's going from the ground up to 100 hectopascals. So right around 17 or 18 kilometers. And you can see
Is 90 south to 90 north, South Pole to North Pole?
Yeah, and South Pole to North Pole, yes.
Oh, okay.
So this is showing what we've observed.
Everything?
Yes, everything. But it's zonal, it's averaged all over the globe, so you only have, you're not seeing it in longitude because it's averaged in longitude. So this is showing temperature changes that we've observed with time, and you can see what the pattern looks like. You have a warming on the surface, and then you have this Arctic amplification, because that's associated with sea ice changes. And you can compare this to what we see in the model world. So this is showing all 20 historical CMIP flights. So this is the intercomparison project I was talking about earlier. And you can look at all of these simulations and look at their average changes. So each one of these simulations, there's multiple realizations. So each one of these groups might have done anywhere from 3 to maybe over 10 what are called ensembles, so different or the same forcings, but they change the initial conditions a bit. So they average over that, and you can see this is the model response for changes. This one can denote the scale on here is different, so this only goes up to 0.3, this one goes up to 0.6, because some of these models have much larger temperature changes. And this is what's shown up here is if we average over all these different modeling groups, so we get this model response, model change. And then what's shown here is if we just perform specified forcing. So here on this one that's called ANT, that means anthropogenic. So if we only have human-caused changes or forcing, so if we only have greenhouse gases, aerosols, and ozone changes, if we only have that going on, what happens in the model world? And then this one similar is NAT, which stands for natural. So that includes both solar and volcanic, and you can see the separate volcanic forcing and also the solar forcing, because there were a couple or a few large eruptions in this time, particularly Mount Pinatubo in 1991. And you also have the solar one, so you can see what happens in these real model simulations where you only have natural forcings. Oh, yes. I don't know why it's going over this again. All right, and the last thing that we need is these unforced pre-industrial control runs. So these are hundreds and even thousands of years of ones where we don't force the climate system at all. So there's none of these forcings. There's no natural, no anthropogenic forcings. And this is just showing time series of the temperature around up here in the lower stratosphere, and on the right temperatures in the lower troposphere globally from all these different modeling groups. And you can see they go around and they wiggle, and you can see the magnitude comparing. So showing from 0 to 15 Celsius how much changes you get. And so this is important because we need an estimate of variability and noise in the system. So how do we do this? So we take these model simulations and then we try to find these fingerprints. And one way to find the fingerprints is this analysis called empirical orthogonal functions. So you can think of it as breaking it up the time series or the pattern that we see into the dominant modes of variability. So this is showing for the anthropogenic signal. You can see what its fingerprint looks like, and then you can compare that to one with all historical forcing. So that includes natural, and then down here is showing the control. So if we take all those thousands of years of control run and we look at what its dominant mode of variability is for temperature, and you can see it looks nothing, you don't get anything like this where you get the warming in the lower troposphere and then the cooling in the lower stratosphere. And it's just showing the different modes, and then you can do the same with the natural only, and that none of these patterns look anything like the ant signal from human caused. Right, and then what we can do with that is that we can search for this fingerprint in observations. I'll just quickly skip through this, but it's going to take a while to explain, but we can search for how strong this fingerprint signal is in observations and compare that to the magnitude of that fingerprint in the control and the natural only simulations we have, and you can see how many times we can get a 20 or 30-year trend in temperatures and the noise, and then compare that to what we see in observations for the fingerprint. And it's just showing that you can look at the signal to noise, and if the signal to noise gets above a certain predefined level, we can identify it as detected. So we've detected an anthropogenic signal in temperatures. And just to give you an example, we found fingerprints of human-caused climate change all over in different areas. So temperature, sea level rise, continental runoff, water vapor. So we're leaving our fingerprint on all these all these indicators. So in summary, these large radiative forcings from greenhouse gases have contributed to a positive imbalance in the climate system, but there's uncertainty associated with aerosols and clouds and how much they've offset the positive forcing. The feedbacks control the magnitude of the response, and it's very, like we saw in that figure, it's very complex. There's lots of uncertainty in the feedbacks and how they interact with the initial forcing. And global climate models are invaluable, and they're a great tool that we scientists use for investigating, and this is what Christoph mentioned earlier, and is the Earth system model in the IGAS, and
What?
What Christoph was referring to earlier for the IGAS? IGSM, yeah.
IGS?
Yeah, global systems model that the joint program uses. So I was touching on the Earth system part of it. And the human-caused effects on climate system can be identified through detection and attribution studies. And like yesterday, I'll leave up some of the resources if you want to learn more, because I can't go through everything in just this one hour, and another link as well to the Global Change site here at MIT for more educational references. That's it, and I'll take some questions. I'll take a few questions.
What are a few sort of hot topic next steps in the modeling world?
Right, so the large one, you know how I showed you that plot and with the errors associated with the uncertainty on the radiative forcing? One of the large things is understanding how aerosols and clouds will respond, or how clouds will respond to climate change. That's because it's very complex, because it depends on the type of particles and also where they are in the atmosphere, and so that's the largest one that they're focusing on. And so they've been building these cloud resolving models, or they can actually resolve clouds. So these are ones that can go up down to 20-meter resolution, and that takes a lot of computational resources. But these are just then they can use the output from these cloud resolving models and try to use that as parameterization into the global climate models. So that's one area people are working on. Any more questions? Yes?
I want to know something about methane, because this is very confusing. Zahova, for example, told that in the Arctic Sea up to 9 trillion tons of the methane hit rate. Rambo, American scientists said this is only 3.2 trillion tons of the methane in entire world, because this is just the question, because if this going up Europe like is in Siberia, Arctic Sea, this will be total disaster.
Oh, so you're talking about sea level rise?
No, the methane, how much is methane under the sea?
Oh, methane, okay. Yeah, so that's one area. So it can be associated with, it's more, if you look at permafrost, because like you said, that's what you said, Siberia, or in Canada, when it warms, then there's methane deposits underground, and those will be released too. So that's definitely an uncertainty. But I don't think it's going to be catastrophic, like you mentioned, but it will be released slowly over time, these methane deposits. And compared to CO2, methane is very short-lived. It's only around 10 to 11 years. Yes, like I showed yesterday, CO2, the lifetime, it can stay in the atmosphere for thousands of years.
It would be so much methane pieces will be last up to 200, 300 years.
Is there any agreement there?
And what, sorry?
Is there any agreement on how much?
How much methane deposits?
Yeah. What time it will be released?
No, that's an area that's like that would add to his question that's being researched. Yeah, how much methane will be released?